Alright, fellas, welcome to organic chemistry. If you're in my class, this is the main thing coming on the end of term test. Okay? So, um, let's begin with a brief introduction. The backbone of organic chemistry is the carbon. Now, carbon is special because its place on the periodic table allows it to have a max of 4 bonds, and it can be drawn like this. Right? Now, it could bond with a variety of things. It could bond with oxygen, halogens. Oxygens and halogens primarily is what we'll focus on, right? So, for example, let's say we had carbon and it was bonded to hydrogen on all of its sides. We have an organic compound with the formula CH4, and we call this methane. We'll go into the naming scheme later on, right? So here's some rules with the bonding. Okay, carbon must have 4 bonds. Oxygen must have 2 bonds, and hydrogen must have 1 bond. Now, another way you could look at it is carbon. Let's go to the periodic table, right? Carbon is in group 6. It could get rid. Okay, screw that. Carbon, it has a tetravalency, which allows it to bond with 4 other things. I don't need to go in depth to it. Just understand that it must have 4 bonds, 2 bonds, and 1 bond here. The carbon compounds are named accordingly to the number of carbon atoms present. So, we're going to explore 2 of the families. We'll explore the alkanes first, the alkane family. Right? Now the alkanes, all of them end in -ene. But before we go into the alkane family, you need to understand something. So we just said that the carbon compounds are named accordingly to the number of carbon atoms present. There are 8 main prefixes we need to know, which are as follows here in the screenshots. Right? We must know that 1 is meth, 2 is F, 3 is prop, 4 is but, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is nonatane. That's verified. I think it's nonatane. C9H20 is nonane. So it is nonane. NON, 9 is nonane, and 10 is decane. So the prefixes there are non and dec. And with these you can name basically everything in the basic end of organic chemistry, which is what we're going to go over, right? So, these are the alkanes. The alkanes only have single bonds present. So based on these rules up here, the carbon must have 4 bonds, O must have 2 bonds, and H must have 1 bond. Now, the alkanes are a family of hydrocarbons. Hydrocarbons only have carbon and hydrogen, and they are considered to be saturated, right? So, let's go in. Let's explore the characteristics of alkanes. They all end in the -ane prefix. I mean suffix. They have the general formula CnH2n plus 2. They are unsaturated. I mean, they are saturated. Not unsaturated, they are saturated. Right? Which means it's the simplest organic compound possible. Right? And only single bonds present. Right? So, let's draw some of these. So methane has 1 carbon. We have the general formula, don't it? So CnH2n plus 2. The n is equal to 1 in this case. So it's CH 1 is 2 by 1 is 2 plus 2 is 4. Ethane C2 2 by 2 is 4 plus 2 is 6. All of them increase in increments of 2 hydrogens. Propane we have 3 C3H 3 by 2 is 6 plus 2 8. This will be C4H10 C5H12 C6H14 C7H16 C8H18 and nonene and decane follows the trend, right? So because they are saturated, it is very unreactive generally, right? What that means is, let's say we had CH4 plus let's say HCl, nothing would happen. However, it could undergo one main type of reaction that we need to know of, and that is the substitution reaction with halogens, which basically means, let's say we have methane, okay? Methane is CH4, and we want to add chlorine to it. It would be Cl2. What happens is, under UV light, what can happen is we get CH3Cl plus HCl. And it follows the same trend. So ethane plus Cl2 gives us C2H5 plus HCl. So basically what's happening is we losing one hydrogen and being replaced with a Cl, and the other Cl, the hydrogen bonds with the remaining Cl. That's what happens. And then, well, there could be a double reaction. So CH3 plus CH3Cl plus HCl could give us CH2Cl2 plus H2. But we basically need to know this part here. Right? Right. Under UV light, this reaction can occur. It could occur with bromine, iodine, any of the halides, any of the halogens. Right? Okay. So that's the alkanes, nothing too deep to it. Let me pull up the C6 syllabus and make sure. Right, okay, my bad. We also have to go into the burning and halogenation. So we went over the halogenation. This reaction is called halogenation. And now we're going over burning. Let's say we had C2H6. And we want to burn it. It is burned in the presence of excess oxygen, 6O2, and it gives us CO2 plus H2O. So it would be 2CO2 plus 3H2O. 4. I didn't balance this properly. Oh yeah, let me go over a tip right here. In order to, when you're balancing organic equations, balance the C first, then the H, and then the O. So let's balance the C's. We have 2 on this side and 2 on this side. So we put 2, then we balance the H. We have 2 on this side and 6 on this side. So we put the 3. And we have 2. We have 4 and 7. We can't put 7 on 2. It's 7 over 2 or 2. But instead we multiply everything by 2. So we get 14, 2, 4, and 6. Right. So this is the burning. This is the complete combustion of an alkane. Now, what is also important is that, okay, ethane might not be able to burn normally. You could burn hexane, heptane, and heptene. Right, we'll go into the alkenes after, my bad. But, yeah, that's not what's important. What's this? Oh, I shift everything down. Okay, so now we're going into the alkenes. We will come back to burning. If you didn't understand, I know I did it pretty bad. We're gonna come back to it afterwards, more in depth, right? Alkenes, alkenes. The difference with alkenes is, well, let's go over some of the characteristics. It ends in the ene prefix. The general formula is CnH2n. It is unsaturated, and there is a double bond present. A double bond present, not two, one double bond. So an alkene would look like this: C double bond C, and then it bonded to everything else. So we have 1, 2, 3, 4. Notice we didn't put 3 hydrogens because it is a double bond. This is 1 bond, 2 bond, 3 bond, 4 bond. Right? So this is ethene. Right? And ethene is the most simple alkene possible. Methane does not exist. Okay? So I have a table with the names and formulas that you should copy and paste, screenshot and take, learn it, rewrite it, do what you have to do, or just learn the general formula of it. It's very easy. Yep. So in alkenes, they have the functional group C double bond C. So this is the functional group. I'm going to draw a longer chain alkene to demonstrate. Right, octane. C, 1, 2, 3, 4, 5, 6, 7, 8. Then it's 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I'm going to draw all those H's. Okay, the functional group here is this. This is the functional group. Right? So because they have the double bond, they are said to be unsaturated because it's more, and alkenes are more reactive than their alkene counterparts, their single bond counterparts. So there's a lot more reactions that could occur. Okay? So let's say we had um C double bond C. We had this element here. Okay? And we wanted to react it with HCl. We would get this. The double bond breaks. We still have the hydrogens. But now there's one more hydrogen and a Cl. We will call this chloroethane. Not ene because the double bond is broken. Okay. Is that it? I think that's it. Yeah. Okay. We're going to go into combustion now. Let's see if I missed anything. Oh yeah, okay. Naming these types of um things formed. Um, so first off, we start off with what it came from. So, well, not exactly what it resembles. So there's 2 carbons, no double bond, nothing else other than the chlorine. So we know we have ethane, and because we have this chlorine here, the prefix for that is chloro. So therefore the name is quite literally chloroethane. However, let's say we had an element like pentene, which looks like this. You know what, we'll go into that when we have isomerism. We're gonna go into the combustion and addition reactions of alkenes, which is pretty straightforward. So we'll go over the combustion of alkenes first. Okay? Let's say we had this reaction. CH4 plus 2O2 gives us CO2 plus 2H2O. Okay, this is an example of complete combustion. Okay, um, so what happens is the methane reacts with the oxygen in the air, and they burn with a clear blue flame. Okay, and in the presence of excess air, this is a reaction that demonstrates complete combustion. Right? If oxygen or air is not in excess, then they undergo incomplete combustion. Which, let's do a bigger one to demonstrate it. 2C3H8 plus 7O2 gives us 6 carbon monoxide plus 8H2O. This is incomplete combustion. Now we can see how this could be a problem. Carbon monoxide is a pretty harmful gas, right? Carbon monoxide is a colorless gas, and it irreversibly, you might know this from biology, it irreversibly bonds with a component in your blood and stops you from being able to like intake oxygen. Well, not intake, but transport oxygen around the body. So it's a pretty deadly killer, and we can see why incomplete combustion could be a problem. It's also a major pollutant, so that's that. Um, when alkenes combust, they also it's basically the same exact thing. The main difference is that alkenes do not burn with the clean blue flame. They burn with a yellow, sooty flame. Okay? Okay. Here's a note that you can read through on your own. There is something called hydration of alkenes. So, okay, here's this. Right, we're going to just look at this. So, alkene reactions are usually addition reactions. When they react with halogens, they form dihaloalkenes. So, we have a pretty good example of it down here. We have ethene plus bromine. The double bond is broken, and we get this, right? And you will notice here that they named it. They named it a 1,2-dibromoethane, right? How do we get that name? That introduces us to isomerism. Actually, time. Okay, 18 minutes in. Wow. Okay, isomerism. This is where we'll stop at for today. Isomerism. Isomers are somewhat interesting, but it's not difficult at all. Um, there's two main things, right? Isomerization. It is here. I'm pretty tired, but I'll still do it. Isomerism. We must understand that isomers have the same molecular formula, but different molecular structures. Okay? So it's the same formula, but different arrangement of atoms. And I'm going to demonstrate that. There's two types. We'll go into that afterwards. Okay? So, let's say we had C double bond C, right? And I'm gonna bother to draw in the H's. The lines represent the H's basically. These lines here at the end of them, right? We would name this just the real name for this. We know that it's butene, but the actual name of this would be butanine. And where do we get this 1 from? We can number the carbons. 1, 2, 3, or 4. But here's the other thing. Let's say we flip that around. C, 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 C. This is also butanine. And that's where the principle of isomerism comes in. The principle of isomerism states that rotation is allowed, especially around carbon atoms. So even if we had something that did look so absurd like this, C, 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 this is still butanine because we can number them 1, 2, 3, 4. And you might be wondering, why is this not but-4-ene? Because what we do is, there's two numbers assigned to it basically. Whichever way is the closest number to the functional group, you go with it. The lowest number that is for the functional group, we use it. So although this is carbon 4, we use the lower one, because that's just how they do it. That's just how the big scientists show you to do it. Okay, cool. So if we had something like this, that this is the exact same as this. Very weird to draw, but it's the exact same. So it could rotate, and yeah, that's isomers. Now, let's see how we could make isomers. Now we're gonna come back to isomers later on, but we're gonna keep it somewhat simple. So let's say we had this. Pentene. And we wanted to find some isomers for it. Now, there's the obvious ones. There's pentuene. There's pent3ene. Actually, no, this is still pentuene. Actually, wait, no, my bad. Pent3ene. It's really the same thing. My bad. Can this still count as pentuene? This could still count as pentuene. But let's say we can change this up even more. We could say it like this. This is an isomer of it. Let's count the number of hydrogens that would be present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C5H10. And what about on it? This is pent1ene. And on here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is also C5H10. But it's not pentene. Because the longest carbon chains that exist here would be here to here. So this is actually some form of butene. I mean, yes, this is some form of butene. And we would call this, this thing down here is what we call a methyl group. And we would call this is methyl, this is 2-methyl, there's always a dash to separate them, 2-methyl butene, 2-methyl 2-butene. Right. Now, careful not to mix yourself up, because this is the same thing. This is the same thing. This is C2. Yeah, is the same thing, right? And another thing, don't get yourself carried away with it, because we could say this, and then put an ethyl group down here, C2H5. This is an ethyl group. And we could say, oh yeah, this is ethyl, this is 2-ethyl pentene. I mean propene. You're wrong, because the longest carbon chain that exists here, let's expand it. Let's expand the F. Oh, there it is. Right. Because the longest carbon chain that exists here is this. 1, 2, 3, 4. In reality, this here would be the rogue of the group. This is a methyl thing. This would actually be 2-methyl butene. Right, don't get yourself tied up with the isomers. Okay. Um right. Maybe we could go over the nope we can't. We have to go over um alcohols. We have to go over organic acids. I'll do polymers in a whole next thing and esters in a whole next thing. Yeah, that's been real stuff for now. Let's look at these others and see if we missed anything. So describe the reactions of the alkenes and the alkanes. Went over that. Characteristic reactions of these to their structures. Um, yeah, so alkenes, I'll just say there, alkenes will always have substitution, and um, alkenes usually undergo addition. Distinguish between alkanes and alkenes. So the alkene has the double bond, relate the properties of the hydrocarbons to their uses. If you wasn't too satisfied with how I put it, there's hundreds of tables available on textbooks that you could get the information from. I can't go over everything if I want to keep these somewhat short form, and we're about to cross 30 minutes. And tomorrow, well, in the next organic thing, we'll go over 3.5, 3.6, 3.7, 3.8, 3.9, and then everything else we'll do in another one. Okay, guys, have a good night.